Well, so I've told it to go live. I have this live stream start thing on, and I'm going to find research to see if the said video has started, and then also test if the I'm restreaming it, but like once this is done, this 3 minutes, I'm on.
Oh,
Yeah.
Right.
Making sure it sounds.
Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah. Yeah. Yeah.
Woo! Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
Hello everybody. How are you doing? Welcome to another episode of Ask Us Anything about Electrochemistry. I'm your host, Dr. Alex Peroff. My co-host, Dr. Neil Spinner, is not with me right now. He is traveling. He may join later, possibly, depending on his schedule. He's traveling in Europe, and it is I think it's about 7 p.m. where he is right now. So please, as I start any kind of live stream, please let me know if you can hear me, if everything is working correctly, if there are any quality issues. Just let me know. I always could use some feedback. As always, I will, this is an episode of Ask Us. This is absolutely episode 22 of Ask Us Anything about electrochemistry, where you can ask us anything about electrochemistry, EIS, cyclic voltammetry, DC voltammetry techniques, AC voltammetry techniques, specific electrochemical systems. If you provide us with enough details, we'll try to answer them. I will get to questions. I see at least one question right now in the chat, so I will get to that, but let me just get through my boilerplate of things. We usually try to run for about 2 hours, roughly, depending on how many questions. If there's not a lot of questions, we'll end early. If there are lots of questions, we'll try to go on as long as we can. Type your questions into the chat, and I'll get to them as soon as possible. There are no dumb electrochemistry questions. Just try to make them as clear as possible. I'm American, so sometimes it may be a little hard if when pronouncing the names of the people who are asking questions. So apologies ahead of time. If you're watching this after the stream has gone live, I will try to have just a list of all of the questions as timestamps in the description of this video, so you can check that out. Also keep in mind that there's usually maybe a 10 to 20 second delay between what I see in the chat and what I present to you. Okay, so keep that in mind as we continue this live stream. Also, if you are a tier 1 or tier 2 YouTube member, you can join us on the live stream. I have made a community post that came out about 30 minutes ago that will give you a link so you can join us on Restream, or join me on Restream. And actually, you could share your screen, you can share your data, you can talk. It's not just typing in the chat of YouTube. So if you are a tier 1 or tier 2 member, click the link and you should be able to join, and I'll be able to guide you along that process. Okay, so we have a question from Priya. Let's get to it. Priya is asking, hi, thanks for answering our questions. Could you please explain about the purpose of imposing bias on the working electrode while performing CV and EIS and how it affects the results? So Priya, I think this is a very good question. One thing to clarify is about what you mean by imposing bias. Imposing bias usually means just applying a voltage or applying a potential. In a cyclic voltammetry experiment, you are naturally adjusting the potential as a function of time. In the cyclic voltammetry experiment, that is the nature of the technique itself. In EIS, you don't have to apply what's known as a DC offset. You can apply a sinusoidal perturbation to the working electrode. But there are things like applying the sinusoidal wave in EIS at some DC offset from, say, the open circuit potential of your working electrode. So, so Priya, also, if I'm saying things and you want additional clarification, please let me know. Okay, so let's just talk a little bit first about performing cyclic voltammetry and what the imposing bias is, how it affects the results of a cyclic voltammetry experiment. And what I'm going to do is I want to share a let me just make a couple adjustments to make sure I don't have any problems, but let me share my screen. I'm just gonna go to handy dandy PowerPoint, and I have PowerPoint up. Good. So let's first talk about cyclic voltammetry, CV, and then what it means to, like, why do we impose a bias in a cyclic voltammetry experiment, and how does that bias change the results? So let's just talk about a redox reaction, right? So let's say I have some kind of thing. They usually use the words like OX for the oxidized species, plus an electron, and that gives me, and usually that's in equilibrium. There is an equilibrium symbol here. I can do that to show you. This is assuming you have a reversible or quasi-reversible reaction, and you have a reduced state. Okay, so let's just say this is my system. So we're doing cyclic voltammetry. We'll also talk about EIS as well. And let me also just check that this is clear. I'm going to hide the question for now just to make sure that people are able to see. So in cyclic voltammetry, what we're doing is we're looking at the we are applying a voltage perturbation as a function of time, and it's usually a triangular potential waveform, some kind of linear sweep. We are sweeping the voltage at some scan rate defined by kind of the amount of voltage that changes per unit time, and we end up getting this kind of cyclic voltammogram. Where the cyclic voltammogram, we're looking at current as a function of voltage, and when we apply a bias, let me just add a little electron there. When we apply a bias, this is the voltage bias prior that we're applying this potential waveform. We get a current response associated with the oxidation or the reduction of our species, and that's what we do. Changing this voltage either through changing the scan rate, so maybe we scan it at a faster rate or something like that. Changing the slope, I would say, can affect things like the double layer capacitance. So you may end up getting a kind of slightly wider voltammogram. That's one thing that the bias changes. But then applying a larger or smaller bias with respect to your working electrode usually means I'm applying a potential that's out in this region or a potential that's out in this region. And so imposing a bias in a cyclic voltammetry experiment is really designed, its purpose is to really scan a range of voltages to see if we get any current to show up. And this current is associated with the oxidation or reduction reaction that is happening in our system. So hopefully, let me try to make sure that Priya, I'm answering your question. So Priya, please let me know if you need clarification. But that's basically CV when we talk about what does it mean to impose a bias on the working electrode. Now, EIS is a little bit different. So let me erase this. EIS, I think, is a little bit different in how we think about an imposing bias. So in EIS, what we're doing is we are, this is time, this is also voltage. We are applying a sinusoidal voltage. This is potentiostatic EIS. This is what we're doing. We're applying the sinusoidal voltage that's usually centered about some point. And we measure the corresponding current. So actually, let me erase a little bit of this so it's a little clearer. It doesn't have to go that far out. Okay. We measure the current. This is another thing that we measure. We measure the current as a function of time. It also has this kind of sine wave as well. And of course, if you're familiar with EIS, you're getting, this may be shifted, the amplitude may be different, and we look at the voltage over the current. I believe that's it. V equals I times R. So voltage over current gives you the resistance, the impedance in the way for a sinusoidal wave. And then we plot it in a variety of different conventions, such as a Nyquist plot. That's the most common type of EIS plot, right? So you get something like this, where you have the quote, the real impedance and the negative imaginary impedance here. All right. Now, when you say imposing bias, this is an imposing bias on the working electrode. That's what we're doing in these EIS and CV experiments. But one thing that you may decide to do is apply a sine wave at another voltage. You may apply it at this voltage, where the sine wave is centered around a higher voltage, a larger voltage. And you may get a larger current. Maybe you get a larger current, you get a different current. And so the question of why would you pick a different voltage for EIS usually has to do with and is related to your cyclic voltammogram. So in your CV, this is at least how I think about it. Let me make this a little bit bigger so people can see. In your cyclic voltammogram, a little bit big, we know that at different voltages, different values, different processes are happening, or even the rate of different processes might be occurring. So if I do my EIS at this voltage here, it will probably look different than if I do my voltage at, say, this voltage, my EIS centered around this voltage. Because at this voltage, there is another process occurring. So there are kind of two different electrochemical processes occurring. And those two processes will, I would say, manifest themselves differently in the EIS spectrum. Different things will happen. Sometimes you may even get the same shape, but the values will be different. So you use this EIS, this Nyquist plot, in relationship and corresponding to some kind of an equivalent circuit. And maybe when you have a different, maybe when you use a different potential, different imposing working bias or working electrode bias, the value of something in this circuit may change. It may be the same system, right? The circuit model, the equivalent circuit, is related to your chemical system, your electrochemical system. So maybe nothing's really happening, like that's physically changing it, but maybe the values are different. And so for example, again, just checking to see if there are any questions. So for example, at this potential over here, let's use green to kind of indicate it. The potential in this region, the charge transfer resistance, which is usually indicated by, say, this resistor in the circuit, is really, really high. It's hard to get current to move, to pass through this resistor at this potential. But if I do EIS at a different voltage here, the value of this resistor will be different. It will be lower. It's actually easier for current to flow through this path at a different voltage, which is different, which is interesting because we typically don't think about these kind of circuit elements that way. We think of a resistance not changing its value depending on the voltage that's applied. Pardon me. But electrochemical systems are different. Electrochemical systems are weird in that way. So all that being said, Priya, I'm hoping that this answers your question. Again, your question has to do with explain the purpose of imposing a bias on the working electrode while performing CV and EIS, and how does that affect the results. So hopefully this gives you a little bit of insight. In EIS, one of the obvious ways it can be shown or demonstrated is that it can affect the result, like the actual value of the capacitance or the solution resistance, or in this case, the charge transfer resistance. That's how it can affect the result. Sometimes you may even have different processes occurring depending on your electrochemical system, if the applied bias is different. And actually, going back, I might make one more comment, which is that, this is for a redox reaction here, right, for my CV system. But if I sweep way far out, I make a current that's going up here. This is a way different process. This can be explained by a totally different circuit. So changing the bias can actually have a big role in actually even changing the circuit depending on the potential that you apply, what your DC offset is. There's a whole lot of stuff like that. So hopefully that was helpful. Okay, and I'm also happy to, if you have a follow-up question related to that, I'm happy to answer it. Let us go to the next question. Keep an eye. Also, first off, hi Kanav. Good to see you on the live stream. Really appreciate it. You did get my my comments just to kind of get this off. I guess I don't want to say off my chest, but Kanav sent me a manuscript to look at, to review. I appreciate it. I'm happy to do that for anyone else who's just curious or who's been on the live stream and asked questions. So Kanav, I emailed you all of my comments and suggestions and criticisms, and I think this hopefully comes through well, but I went through it's a lot of stuff that I made recommendations for. And sometimes I know people can take criticisms very personally, and it never feels good to get them. But I just want you and really everybody, if you are writing a manuscript that involves a lot of electrochemistry, it's hard. The first time you write a manuscript, even the second, third time you write a manuscript, it's hard. It's not an easy process, and there's a lot of little kind of nitpicky things. But really trying to help people, and sometimes, hey, a lot of manuscripts and publications get rejected, and I'm trying to make sure that you don't have to go through that process. You can you submit a paper to an editor with the best quality, so you have the highest likelihood of not only getting it accepted, but also making sure that you're doing good science as well. Just personal stuff, opinions. So continuing on with the questions. Okay, so this is from Barry. Barry, good to see you as always. When would someone benefit from a rotating ring disk RRDE electrochemistry? Barry, this is a great question. So the most common benefit or use of the rotating ring disk electrode by far is for the oxygen reduction reaction when you are developing catalysts. And let's kind of share screen so that I think it's a little, I may have some things available, but let's take this the same kind of system. Let's take a look at this. So let's say I actually had a couple reactions. Let's say I can't. Oh wait, it's not allowing me to. I'm just gonna make a copy of this. Let's say you had red on this side, and red also had another electron transfer to we'll just call this else because it's creating something else. Make this big. Most of the time, right? I've drawn these as equilibrium expressions, but there is a kind of a rate associated with them. And so some people in a ring disk experiment will try to kind of rotate the electrode such that quickly enough that they can actually extrapolate some kinetics and maybe even oxidize this reduced species back to its oxidized form before it undergoes a second electron transfer from red to something else. So this is typically used for the oxygen reduction reaction. And let me go to review. I mean, maybe it would be just easier for me to talk about it. And for people who are unfamiliar, a rotating ring disk has some kind of glassy carbon disk electrode. There is some kind of ring that's around it. And that ring, actually, I'm making life difficult for myself. We have tools that already exist in PowerPoint that will make it a little bit easier just to kind of make sure people. So I'm going to send this to the back. I'm going to make this a different color. All right, make this somewhat concentric. I'm going to paste this. I want this for later. And actually, I'm gonna paste this again. Gonna make this a different color. Let's say I make it orange. And bring it to the back. So I'm just gonna create a rotating ring disc electrode here. Let's say it's gold. Let's say gold is the color, and then this is the shroud. The shroud's very big. All right. That's actually not a bad rotating disc electrode. So this is the disc material. This is the ring is this gold here. And usually you want to use a rotating ring disc when you have, when you generate a species and then it gets maybe oxidized or reduced at the ring. And so usually this helps you, right now its primary purpose, the rotating ring disc, is for oxygen reduction reactions, where you have, where ultimately the O2 reduction is a four electron transfer process. There's a bunch of protons involved. I think there's like about 4 H plus, and this gives you water. Sorry, there's 2. And there's 2 waters. So this is the reaction that's occurring at the disc electrode. But sometimes you have a 2 electron transfer process with 2 protons. And this gives you peroxide. So H2O2. And you can oxidize this at a ring. And that's a way to determine the collection efficiency, or not the collection, the catalytic activity, sort of say, of your oxygen reduction electrocatalyst. Let's see. Oh, wait. Okay. I am checking. Let's see. Audio is cutting out. Chris is saying that the audio is cutting out. Chris, give me a little bit more feedback. Is it still cutting in and out? Also, if anyone else can, I'll have to maybe figure out if something's going on with the, we use a Focusrite audio thing for all of our audio stuff. But I'll also have to check this out when I'm doing stuff. So Barry, I hope this is helpful. There is also, if you are curious, there are other benefits to using a rotating disc electrode, not just a rotating ring disc. The rotating disc electrodes, in a way, allows you to do these kind of kinetic studies with your system. So that is, yeah. So that's kind of another. That's another use of a rotator, is to actually get things like the heterogeneous rate constant. Actually, the heterogeneous rate constant is the only thing that I know. Okay, all right, Barry saying the audio is good now. Okay, thank you. I wonder if that had to do with just talking into the mic. So, and Barry, please let me know if that answered your question as well. I'm also trying to talk to the webcam, but also talk to you guys and talk here and there. So just take my time. Okay, continuing on. Winnie. When determining the activation energy to a specific fitted resistance via an Arrhenius plot, why does the inverse of fitted resistance correspond to the rate constant of a reaction? Let me look up an Arrhenius plot, because I'm actually not too sure about fitting the resistance. When you say that, Arrhenius plot. So Arrhenius plots, to my knowledge, don't have a they don't have a resistance associated with them. I might need talking about. Let's see. And Winnie also mentions talking about temperature dependent EIS, if not clear. Okay. So, okay. Temperature dependent EIS. Yeah, I think I'm getting a little bit held up on the whole Arrhenius plot. But, so the activation energy of a specific, why does the inverse plotting, why does the inverse of the fitted resistance correspond to the rate constant of a reaction? So, Winnie, correct me if I'm wrong. The thing that usually comes to mind when talking about this is looking at the charge transfer resistance from a Nyquist plot. So the charge transfer resistance is just a representation of how resistive a Faradaic reaction, maybe it's like just how much of a Faradaic reaction, how easy it is depending on the potential. So let me just get your question up one more time, because as you adjust the potential, as you get closer to the redox potential, the resistance associated with a reaction decreases. And also, as you change the potential, the rate constant actually changes. The rate of a reaction changes. And let me actually think. No, the rate constant actually remains the same. So the rate constant should be fixed for your system. Of course, temperature dependent EIS. You know, Winnie, I might not know exactly how to answer this question. I'm trying to think about it and figure out what. But it's very interesting. I feel like I know a lot of the parts and pieces to it, but I'm not seeing exactly the correlation, or I don't know the equation associated to the fitted resistance. The inverse of the fitted resistance corresponds to the rate constant. Like, I don't know if there's an equation. There probably is an equation that relates some of the resistance data to the resistance data. Let's see, resistance to rate. Yeah, I'd have to think about this. I'm sorry if I don't have a great kind of answer. I think conceptually, yeah, if you're doing EIS, maybe even like, I understand how the rate of a reaction will the rate of a reaction, or the rate constant. Let me see. Yeah, the rate constant will increase as the temperature increases, based on the Arrhenius equation. I don't quite know about the resistance. Let me try at least to describe everything that's kind of going on in my head about this. So maybe we can at least think about the system. So if I go here, I'm going to delete all of these things. So if I have Winnie, if I have a redox system, all right. So let's just get, this is similar to the kind of the first question. If I have a redox system, I have my cyclic voltammetry, And if I have my EIS data, looks something like this. And I model my redox system as a resistor for the solution resistance, a capacitor for the electrical double layer, and then I have this resistor here, which is associated. It's associated with the charge transfer resistance. So let's make this kind of yellow, and then this is this is make this thicker again. Why does it always default to that? This is the charge transfer resistance. Okay, so this is the charge transfer resistance. And as the potential increases here, VI, this value decreases. And so the resistance value decreases. And I don't know if this is related to what you're looking at. And similarly, as you increase the temperature, the resistance for charge transfer also decreases. The rate decreases. I am not super familiar or haven't been able to relate this to an Arrhenius plot where, the rate constant is related to the activation energy times E to like the minus, or I think it's like EA. Let me get the Arrhenius plot out. A to the, so it's not EA, it's A to the, so it's the Arrhenius expression. It's actually something more along the lines of A. Oh man, I hate how this is not, doesn't default to the thick thing. So A, just the constant, to the minus EA over RT. So this is the rate constant, which is a constant. It is a function of the activation energy and the temperature. Perhaps the activation energy, I think, is more or less a constant. You overcome activation energy barriers, but the activation energy itself, I want to say, is a constant thing. Or maybe it changes based on catalysis. But that's what happens when it comes to electron transfer and the rate constant. These are the kind of relationships that I'm thinking about, but none of these actually have to do with sorry about that. Please don't. Okay, so Barry, yes, let's chat. I'm gonna talk about what it requires to buy or purchase a rotating disc or rotating ring disc electrode. So I'm just gonna type in the email. We're at pineresearch.com, and either myself or Neil or someone can help you with like the purchasing and what's needed to do a rotating ring disc experiment. And we're more than happy to do it. So Barry, just let them know that you talked to us on YouTube, and the person who normally looks at PineWire typically will kind of help with that process. All right. So hopefully this may be a kind of short episode if I don't get any further questions, but that's okay. I think it is September. September timeframe. People are getting back to school, back to classes, back to doing research. There may be questions, there may not be questions. Either way, myself and Neil will make ourselves available for the next next few minutes or so. If you have any questions or comments or just anything that you'd like to say, I'm more than happy to talk about them while we're here. In general, a couple of things to keep in mind. I think Neil will be back next week. I believe he'll be back next week for the live stream. If you have questions about batteries and more EIS related content, I'll probably be out the following week, and Neil will be in charge. But we'll make sure that we continue making these live streams for those who are interested and have some electrochemistry questions that you're interested in us answering. Also, please let us know about content quality and things like that. We're happy to have these types of conversations with you guys. We enjoy them, and let us know if there's more clarification that you may need in answering some of these questions. Hopefully we've described a lot of these things or answered a lot of these questions as time goes on. In other news, let's see. Are we getting other questions? Let's see. Okay, so we have a new question from Kishitij. Sir, what do you make of a Nyquist plot which majorly shows a linear line? That's a very good question. So I think there's two things to think about when you see just a linear line in a Nyquist plot. So I'm gonna again share my screen. I'm gonna lasso tool erase these. There's two things that kind of come to mind when you mostly have a line. There's kind of two lines that I'm thinking about. All right, so these are both Nyquist plots. This is Z real. This is Z negative Z imaginary. So I'm just going to type this kind of both. Imaginary and then Z real. Okay, so there's the kind of Nyquist plot that's like this. It's a straight vertical line. And when you have a straight vertical line, that usually means it's a capacitor. This is the response of a pure capacitor. All right, and that's, that's just this symbol. So when you have a line that's, there's no like Z real, it's all Z imaginary, it's a straight line like that, it usually is just the impedance of a capacitor. As the frequency gets smaller and smaller as you go up, the impedance increases. Now the other thing, if you have a line that looks kind of like this, right, and maybe this is the line that most people are talking about. My experience with getting a result that looks kind of like this in the Nyquist plot is that you actually have a semicircle. You have it way down here. It's just super, super small compared to the impedance here. So you have this kind of low resistance, or maybe a small RC circuit. This is still the same solution resistance, which has to do with this distance from here to to 0. And then you have another charge transfer resistance. You have a capacitor. And really, like, the size of the semicircle, I believe, has to do with the size of this resistor. And most of the response, low frequency response specifically, is all in this line. So hopefully, so that's what I noticed when it's like you just have a linear line in the Nyquist plot. Let me also try one thing. I'm going to see. Let me also share another screen, Aftermath. So I'm going to try to do. Can I do circuit simulation? I just want an RC circuit. Okay, so I have this RC circuit, and I'm just trying to remember if the resistance gets smaller and smaller, this value gets lower. In fact, you may not even get a full semicircle. So another thing that could happen is that I'm not putting the Warburg diffusional tail, and hopefully, let me just make sure you guys can see aftermath. Right. So as the charge transfer resistance gets smaller and smaller and smaller, these values, these are like single ohm values, they're tiny. I mean, and if you say let me see if I can do this. If I do another circuit simulation, but I have a traditional RC, no, I need a Warburg. I think I need to have a Warburg element in here. I'm going into uncharted territory for my own knowledge, but resistor, charge transfer resistance. Let's use Q. Or no, let's not use Q. Let's use a Warburg element. So let's see what this gives me. And maybe what I need to do is maybe I need to put this in parallel so that the circuit works. Let's just call it test. Circuit is invalid. Did I not? Maybe I need to disconnect this. Delete this component. Oh, I think I see what I did. Yeah, I see what I did. I need to put the Warburg back in. This goes to here. This goes to... let me delete a couple parts. Oh, let me disconnect from the right. And let me also disconnect from the left. So I want these two to be parallel. I'm not doing this correctly. Neil's going to be very disappointed in me as I try to put this circuit together. Okay, now let's see. Circuit's valid. Good, I managed to do it. Hooray. Okay, yes. All right. Okay, so I have this circuit, and let's go to home. And I think depending on the Warburg element. Nope, I don't know enough about actually creating that diffusional tail. All right, well, never mind. I actually don't know enough about it, but I'm pretty sure. I'm pretty sure the idea is you get this Warburg diffusional tail. Again, Neil is really the expert when it comes to these. I think I need like another semicircle to try to like show this, but hopefully the image, hopefully the idea still applies. That the reason why the majority of your Nyquist plot is a linear line is because the diffusional component is making a massive contribution compared to the semicircle. The semicircle is super small. So, Kajit, sorry. I hope that was helpful. Okay, alpha portal. Can a programmable DC power supply be used instead of a potentiostat? And there's a second part. Only for maintaining constant potential difference. And if yes, then what all points to take care of? So it's only for maintaining a constant potential difference. So alpha portal. So a programmable DC power supply can be used to apply a voltage to an electrochemical system. That's fine. But the ability to maintain a constant, I would say, real potential, it will not work. It depends. But I can talk a little bit more about either why it doesn't work or what things you need to consider. So, so when you have let's just say you have two electrodes. You have one oh man, I hate why this doesn't default to 4. Let's say you have two electrodes in solution. Okay, so I just put this, some water. This goes out, and there's some water here. And there's maybe, and you apply some kind of power supply, some voltage to both sides. Maybe that's like a constant, like 5 volts. Well, if you're applying a constant 5 volts, that's not a problem, right? You'll always have a 5 volt difference between these two if you were to do this thing. You'll have oxidation reactions occurring on one side, and you'll have reduction reactions occurring on the other side. So oxidation and reduction, you'll have charge balance. And you can do that. That's a perfectly valid electrochemistry experiment. But if I had, say, but the thing is, the potential, the potential of these kind of individual electrodes by themselves is not constant, sort of say. Because oxidation and reduction reactions are happening, the individual voltage is not the same. So if I put a reference electrode into this solution, okay, let's say it's like silver chloride. This is just kind of what reference electrodes look like. It's a little frit. And I were to measure, I would use a voltmeter. So this is some kind of voltmeter. Or I can measure, it's a dial, I measure different values. And if I hook this up to here, and if I hook this up to here, I would measure a constantly changing voltage. This would be constantly changing. As current is passing between these two electrodes in the form of ions moving back and forth, then the voltage at this electrode is changing with respect to a constant voltage. Okay. You have a constant voltage between these two, but the voltage of these kind of with respect to something that's not changing, because this is changing and this is changing, that's kind of why you need a potentiostat. Now you could have a voltmeter and a power supply, and then you could see how is this voltage changing on your voltmeter, but that is but that's really, that's what you can do. The voltage will constantly change if you don't use it. Like a potentiostat utilizes feedback to maintain a voltage between a constant voltage set point and your electrode. But having, just doing something to get oxidation reduction reactions happening, you don't need a potentiostat. You just need a power supply. And let me just say, for maintaining a constant potential difference, you'll have a potential difference, but it doesn't mean that those things are constantly changing. But their voltage difference will be the same. So hopefully, Alpha Portal, this answers your question. Kanav. Okay, so Kanav. All right, so Kanav is asking, what was your honest opinion of the manuscript, Alex? Like, out of 10. It's for me to gauge how much I need to improve. Okay, Kanav. So, all right. Okay, Kanav. So, I'm going to preface this again by saying that I was a very bad scientist when I was first starting out, and I didn't really know a lot of things. But I unfortunately, my kind of brutal and honest opinion of the manuscript is that with a 10 being the best, super high quality, not a problem, all that kind of stuff. Unfortunately, I think it's close to like a 3, maybe a 2 or a 3. And I provided some feedback to you in your email, as well as in the manuscript. And I'll explain to you, and now that we're kind of not in email land, and I can just talk to you as a normal human being and not with just like formal language, I'll give you my kind of like my honest take of the manuscript, my thought about it. And first and foremost, let me describe what the manuscript is about, so that if I'm describing it incorrectly, then you can correct me and you can say, "Ah, this guy doesn't know what he's talking about. He didn't get the point of the manuscript." But what it sounds like is you did a lot of electrochemistry experiments on some graphite electrodes, some graphite rods, actually, just graphite, like pencil graphite. And you did some pre-treatments using water and nitric acid under a variety of conditions, having them soaked, having them rinsed. And then you did cyclic voltammetry to oxidize and reduce the graphite, forming graphene on the electrode surface. And this graphene is useful for, has applications for vanadium redox flow batteries. That's kind of the point. This paper is in many ways a synthesis paper. You're describing the process of what you're doing, of this process, and it can be useful for other people and who are doing redox flow battery research, and that can be useful, right? We're trying to we're trying to provide information that's helpful to other scientists in the field. So one thing that I noticed first off with the manuscript, and I know people, this is probably only really useful for Kanav. I'll try and make it a little useful for other people. One thing that was interesting was that throughout the manuscript, in like the introduction and the abstract, there was this emphasis on its application for vanadium redox flow batteries. And there really wasn't very much experiments done on the vanadium redox flow batteries. And you sent in an email, you said, you don't have the vanadium salts to actually do some experiments. And I totally get that. That's fine. But one piece of advice, and this is, and just to kind of set the record, the first manuscript I submitted for publication was rejected. It was rejected. It took me a year rewriting the paper more to actually get it submitted. And the reviewer gave me a very unique bit of advice, which was that one problem I had in the paper was that I was comparing my work to someone else's work. But I hadn't done all that other person's experiments. So the reviewer rejected the paper because, like, hey, you're trying to compare yourself to this other person, but you haven't done the due diligence of being able to reproduce what this other person did to make an honest statement. And truly, it makes sense. Oh, Chris is dealing with escrow. Oh, yeah, escrow sucks. Chris, I'm sorry. That's rough. Yeah, deal with the escrow. I hate escrow sometimes. But what it taught me, the feedback from the reviewer, was that you should write a paper based on what you did and not based on what other people are doing. So I hear all this stuff about, redox flow batteries and stuff, and it's like, well, there's no redox flow battery stuff. Well, you can say, at least for motivation, that like, hey, we're doing this because it could be useful for redox flow batteries, but just leave it at that. Like, don't keep using redox flow batteries as like the kind of the crux that you're doing this for. Like, show that you did something that was very, very cool, and very useful. There were a couple. Now, one thing as a scientist was like, all right, so you say that you have graphene on the surface. How do you know that? And you address this in your email to me, Kanav, saying that, like, there's some stuff in the literature, and that you're even thinking about doing some experiments like Raman or XRD to demonstrate that you have graphene on the surface. I think that demonstrating that you actually do indeed have graphene is important. I think that that's an important thing in your paper. is actually saying, hey, I actually do have graphene because I have I think it's like the 2D band stretching and like the Raman or something like that. So that was one thing from a science perspective that I do think an editor is going to point out in your manuscript. Another thing is that there is I mentioned a few choice of words with like the language that's used, with like, little things, grammar and like spacing. So make sure that there's proper spacing and signs with like voltages and units so that there's a space between the units. Chemical symbol, chemicals need to be like lowercase. There's, unless they're starting a sentence. Those are little tiny things that they don't bother me that much, but having gone through the process, it's like, all right, I have to keep an eye on it. Kanav, I would encourage you to use, and my advisor in graduate school was always attacked me for, not attacked me, but criticized me for this. Like, this was a thing I needed to improve on. Was I would say things like, the current was higher when I bubbled CO2, or that was my experiment. So when I did this thing, the current was higher. Well, don't just say that the current was higher. Say that say the current was higher by a certain amount. Like use the data to indicate quantitatively what is happening. Right? That's an important thing. Like use the data. Like, oh, the current went up by 1.5%, indicative of enhanced catalytic activity. Like use a number. Don't just say the catalytic activity improved. Say that it improved by a certain amount, and then why is that important? What does it mean? Now, one thing that I have learned as a scientist at my job at Pine, not so much when I was a graduate student, Kanav, is something called UX, user experience. And Steve Jobs was really kind of the pioneer of user experience. Like when you have a product, when you have a thing, how do you make it as clear to the customer, the end user, as possible? So, how do you make it as clear to the person as possible? Like what it is, how does it work, things like that. And I think about that now, like, okay, how do I make, like, you do a lot of experiments, a lot of different preparations, a lot of different, you have pre-treatments and different cycles of your graphite electrodes. But there's so many iterations of it. How do I make it clear, not just in words, but maybe a graph would be the easiest way to show what's the difference between this guy and this other guy and what their names are. And so something like developing that clarity with like what all the things are, and like you may categorize it in your head one way, but you have to also think about, well, what's someone who's never seen this before? How would they interpret or look at this data? And Kanav actually made a comment. Let me just read this. So from my understanding, there are two major things to change. One, reduce the emphasis on mirror unless I have experiments to back it up. And two, backing up graphene production, like I said. Yes. So Kanav, yes, I would say those are two major things. Those are things that, so reducing the emphasis on vanadium. Chris just said something. So there's I understand there are two major things to change. Yeah. So so the emphasis on the vanadium redox flow batteries, unless you have experiments where you're actually using vanadium salts and you're showing improved electrocatalytic activity or electrochemical activity via more current compared to something like graphite, then like, yeah, I would try to minimize how much you talk about that in the paper. But at the same time, if you do the experiment where you're testing a vanadium salt and showing that you get more current for it, that is above the norm, sort of say, taking area into consideration and stuff like that. Yeah, so that's one thing. And then, yeah, I think an experiment that independently shows that you really do have graphene on the surface is very important. Yeah, XRD or Raman, something that just, yep, I have graphene. It's well established that this peak means I have graphene, and I can show when I do XRD of graphite, I don't get this peak. So I think that's another important thing. Yeah, the other is nomenclature and quality of life for reader. Yep, absolutely. I think a lot of people try to make, sometimes they make papers super complicated and super confusing, and I hate it. Make it so that as many people as possible can read your paper, because I'm sure someone's going to be able to cite it more often if they understand what's going on. So yeah, there's a nomenclature quality of life for the reader with all the different variations of cycles and pre-treatment to the electrode. And also, I think there may have been some cases, like I understood, like, okay, you have the electrode pre-treated for 2 days in nitric acid, and then 12 days in nitric acid. But then I didn't know what the cycles were. Like, what does this? I thought it was like maybe like 2 cycles or more cycles. But so yeah, just clarity of like what each of these things are, and you can always have supplemental information if that information doesn't make it into your into the manuscript itself. So yeah, those are a couple, I would say, big items. Yes, yeah, yeah. So if there's another paper that used this very same technique to demonstrate it, yeah, you can reference this paper. And I haven't read the literature, so I do not know whether or not that's the case. But at the same time, if another paper has proved that you can make graphene with this procedure, then what is your paper really about? Right, that's another that begs the question on another thing. Is this a novel technique for generating graphene that can be used for redox flow batteries on pencil pencil graphite, for example? Yeah, I've definitely used cases where like, oh, this is demonstrated in the literature, so I know very clearly that like I do have graphene on the surface. So yeah, I don't know that much about the literature from that standpoint. Another thing, I assume you're going to do this, I'm not sure, but you took some screenshots of your cyclic voltammetry data as well as SEM images to come up with some, to put some figures together. So those figures, I think they need to be made very clear. Like you may have a ton of data. You're probably going to need to format those figures, maybe not the SEM images, but the CV data should be formatted, because the legend is very difficult to read. And you may need to format so it's different shapes so that people who are colorblind can also read your paper, because if it's in different colors, someone who's colorblind is not going to be able to read it. So you may have to make it into shapes of triangles or stars, stuff like that. And make sure that your data tells a story. I saw a lot of, what was it? There was that, and there was also, like, yeah, I saw SEM images of like flakes and stuff like that, but it's not clear, like, okay, what is the data telling me about, yeah, I see that my other comment was also that, okay, you have this data, you want to use as much quantitative terminology to describe something. It was like, I have stuff like, thank you. This makes a lot of sense. Big takeaways from this. Thank you a lot for the honest, no holds barred. Good. I'm glad you appreciate it, Kanav. I sometimes receiving feedback is always very hard. It feels like a criticism of who you are and your character, but it's not. It's not that at all. And and basically, I always say, like, if you feel that way, give yourself a day. Just give yourself a day. Don't don't think about it, and then the next day, usually you feel pretty good, and you're like, okay, I had a day, I got the feedback, and now, and more often than not, when you apply some of that feedback, it's not even that painful applying some of those comments and criticisms and feedback. Your paper gets better. Your paper will be objectively better by incorporating some of these things. And you can use it for all your future publications, your future papers, things like that. I'm trying to think, because I wrote all these things down. I think I had it all yesterday. But I do, I made a note that one thing I did a lot of, and I just described, was I used a lot of wishy-washy words like something's higher or something's lower. Use quantitative descriptions. Also, you may use, let's see, if you're really a scientist, if you can't take feedback, yeah, that's right. You really need to, you need to be able to take some feedback on your experiments if you're a scientist. Absolutely. I think another kind of somewhat big thing, if it didn't come through in the manuscript, was I thought your results and discussion, I thought your conclusions, the first few paragraphs of your conclusion are really good, but I think that they belong in the results and discussion. Like I think, like you said, like the current was this at this potential, and the current was that at this potential, which means these kinetic things. I'm like, that is a results and discussion thing. The conclusion is just a paragraph or two about like the big picture, doesn't require any quantitative descriptions of stuff. Like I thought that just needed to really be moved with a little adjustments. Yeah, all the quantitative stuff should be there. Yeah, I think that was it. I think at the end of the day, I want to see more concrete language about what exactly does your thing do. Don't use things like the cathodic area. Use like between this voltage and this voltage, this was observed, which indicates this, and it's very like straightforward to the point. Use your figures also to guide the reader to what you want them to see. Like I want them to see that the current was really big, that the current was really big, and that was so much bigger than this other one. Well, sometimes you don't want to have 5 voltammograms if you want to show the difference between two things. Maybe you split them up, that kind of thing to really emphasize what you observe, what you don't observe. So Kanav, absolutely, I'd be more than happy to see an updated draft. I will try to get back to you as soon as I can, but I can't make promises. And please let me know if you have any further questions about the draft, about the paper. It was fun reading it. It was definitely fun reading it, and kind of learning a little bit more about what you're doing. But again, I'm a chemist. Neil's a chemical engineer. The purpose of the paper and what's the end take-home message may be different between the two of us, but those are some things. And I don't know what your relationship with your advisor is like. You can bring these comments to your advisor and let him know what he thinks about it as well. But yeah, I'm more than happy to take a look at it again. It may be a faster read because I actually will know what you're talking about. Yeah, think about how people tend to read papers. They read the abstract, the browser figures, read the conclusions, and then the results and the rest. Yeah, people read papers in they read them. They look at the abstract and all that kind of stuff. Yeah, the figures I think are also just super important. Spending time making really nice figures is good. Yeah, they look at the conclusion. Yeah, then I look at the results. Yeah, it's kind of funny how the ordering with which people read these things. So yeah, that was good. I'm glad we had a chance to kind of talk this through, and hopefully I'm glad you're also taking it well. Feedback's always tough. Sometimes I hate getting feedback, but again, I just give myself a day, don't even think about it, and then I come back to it, and it's like, okay, let me start incorporating this stuff, and the paper will be better. It has a higher chance of getting accepted. Let's see. As a matter of fact, I showed him your feedback, and his exact words is, "That's great." He said, "Send me an update." Oh, okay, very cool. It's nice because sometimes, I'm not in academia. I'm not in academia, so it's nice to know that the professors still think that what I say is correct. It's nice to have validation from the professor. I'm not really a professor. They're on a higher level than me, so I'm just I have a PhD. I'm just a lonely sales scientist. So thank you, Kanav. I appreciate that. Yeah. Well, we'll work together on this whole thing, and whatnot like that. Very good. Very good. Okay. All right. Well, with that said, it doesn't look like there are any other questions right now. Of course, you can always email us. We'll have another Ask Us Anything about electrochemistry live stream next week. And with that, I think I will wrap up shop, and I hope all of you have a wonderful weekend wherever you are. And we will see you later.